Welcome! Today we're diving into finite automata, which is a really fundamental concept in the theory of computation. If you're prepping for your semester exams, you're in the right place, because we are going to break down everything you need to know in a simple, clear way.
So, let's start with a big question. You know how a compiler can spot keywords in your code, or how a search engine instantly finds text in a huge document? How do machines actually do that? How do they understand patterns? Well, the answer lies in something called Automata Theory. So, here's our game plan. We'll kick things off with the basic theory, then cover the essential definitions you absolutely need to know. After that, we'll compare the two main types of automata, and we'll wrap up with a practical example to see how it all works in action. First up, what exactly is automata theory, and why is it such a cornerstone of computer science? Let's get into it. Okay, in simple terms, it's the study of abstract, self-operating machines. We use it to figure out the limits of computation. What problems can computers actually solve, and what problems can't they? You should definitely make a note of this definition. It's a classic exam question. At its heart, it's all about creating mathematical models for computation.
As you can see here, automata theory isn't just its own little island. It's one of the three core pillars of the theory of computation. It's really the foundation that deals with defining these mathematical models of machines, and that's exactly what we're going to focus on.
Okay, next section, let's talk about the language of machines. To really get how automata work, you first have to understand their vocabulary. So pay close attention here, because these basic terms, they're going to pop up in almost every single exam question on this topic.
Everything, and I mean everything, starts with a symbol. It's the most basic unit you can imagine, just an individual character, like a letter, a number, anything. It's as simple as that.
Now, an alphabet, which we denote with the Greek letter sigma, is just a finite collection of those symbols. It's basically the set of all characters our machine is allowed to work with. A super common example is the binary alphabet, which is, you guessed it, just the set containing 0 and 1. Okay, so what happens when you take some symbols from your alphabet and arrange them in a sequence? You get a string. Now, here's a really important one to remember. The empty string, which we write as epsilon, it's a totally valid string, it just happens to have 0 symbols in it. Don't forget that one. And finally, we have a language. A language is really just a set of strings that all follow a specific rule or pattern. So, for example, you could have the language of all binary strings that start with a 0. And a language can be finite, with a specific number of strings, or it can be infinite. All right, now that we have the vocabulary down, let's get to the main event. Let's build the machine itself, the finite automaton, or as you'll often see it, FA. Think of a finite automaton as a very simple machine. It has limited memory, a set of states it can be in, and a bunch of rules for moving between those states. Its entire job is to read an input string, one symbol at a time, and decide if that string belongs to a specific language. It gives a simple yes or no answer. It either accepts the string or it rejects it. Okay, listen up, because for your exams, this right here is absolutely crucial. Every single finite automaton is formally defined by these 5 components, what we call the 5-tuple. You have Q for the set of states, sigma for the alphabet, delta for the transition rules, Q0 for the one and only start state, and F for the set of final or accepting states. You really have to know this. So, how do we actually visualize one of these machines? Well, there are 2 main ways. On the left, you see a state diagram. It's basically a graph where the circles are states and the arrows are the transitions. And on the right, you have a transition table. They both show the exact same information, how the machine moves from state to state based on an input, just in a different format. Now, finite automata come in 2 main flavors, and I can almost guarantee you'll get an exam question asking you to compare them. So let's break down the difference between a DFA and an NFA. The key word here, the one you have to remember, is deterministic. A DFA is deterministic because it knows exactly where to go next. For any state it's currently in and any symbol it reads, there is one and only one possible next state. There's 0 uncertainty. Now, with a non-deterministic FA, or NFA, things get a little more interesting. For a given state and input symbol, the machine might have multiple options for where to go next. It's like it can explore several paths at the same time. This flexibility often makes NFAs way easier to design, even though they're more of a theoretical tool. This table is a fantastic summary of the differences, perfect for your notes. But the most important part, the real core difference you need to understand for your exams, is that transition function. For a DFA, it maps a state and an input to a single next state. But for an NFA, see that 2 to the Q? That means it maps to a set of possible states. It represents the power set, all possible subsets of states the machine could jump to. That's the critical distinction.
Okay, theory is great, but let's actually see how this works. We're going to take a simple DFA and trace an input string through it step by step to make this all crystal clear.
So here it is, a simple DFA. Its entire purpose in life is to accept any binary string that starts with a 0. You can see the start state, Q0, has an arrow pointing to it from nowhere. And the final or accepting state, Q1, is the one with a double circle. So let's test it with the input string 010. All right, let's trace this together. We always start at the initial state, Q0. Now, we read the first symbol of our string, which is 0. The arrow for 0 from Q0 tells us to move to state Q1. Easy enough. Next, we read 1. From state Q1, the arrow for 1 just loops right back to Q1, so we stay put. Finally, we read the last symbol, another 0. Again, the arrow from Q1 loops back to itself. And that's it. We're at the end of the string. So, after all that, where did we end up? We're sitting in state Q1. Now for the final check, is Q1 an accepting state? We just look at the diagram. Does it have a double circle? Yes, it does. And because we ended in an accepting state, the string 010 is officially accepted by this machine. So why does any of this matter? Well, this isn't just some abstract theory. Finite automata are working behind the scenes all over the place. They're in the compilers that build your code. They power the find and replace feature in your text editor. They're used in network protocols to analyze data packets, and they're even the foundation for designing digital circuits. And that wraps up our introduction to finite automata. But I want to leave you with one final thought to chew on. We know that for every NFA, you can build an equivalent DFA that recognizes the exact same language. So, if that's true, why do we even bother with NFAs in the first place? What's the practical advantage? Something to think about.